Welcome back to our discussion on surface chemistry. This is our fourth meeting, and when we finished last class, we were looking at the pre-exponential factors of a catalytically converted ethylene in the presence of hydrogen to ethane, and we showed that for various catalysts, these are all metallic catalysts, the activation energy is the same, but the logarithm of the rate constant is different. If the logarithm of the rate constant is different, because of this difference in the logarithm of the rate constant, what it implies is that because the EAs are the same, implies that A is different. So, in this set, what we see is that the activation energy is the same, but the log k's are different, and the log k's being different implies that the pre-exponential factors are the same. And here you have what is the activation energy for this reaction in the absence of a catalyst. In the absence of a catalyst, this activation energy is 145 kilojoules per mole, whereas in the presence of any of these catalysts, it is almost a factor of 100 kilojoules per mole less. So, these are all provide a decrease in the activation barrier for this conversion of ethylene to ethane. But each of these catalysts have a different rate of the reaction. So, this rate constant different means that the pre-exponential factor is different, and we were trying to explain what is the reason for this difference in the pre-exponential factor. In the gas phase, imagine that you have C2H4 reacting with H2, you have a bimolecular collision to give you ethane. Let us imagine that this is it, and A in this expression is related to the bimolecular collision frequency. So, if the catalyzed reaction has to go faster, then we know that EA is smaller. So, EA catalyzed is smaller than EA uncatalyzed, but A of the catalyzed reaction is usually less than the A of the uncatalyzed reaction. What is the reason for this? Let us try and understand this quickly. Consider that we have a catalyst in some reaction vessel. So, that is my catalyst surface, and I have ethylene and I have hydrogen here. Now, on the catalyst surface, I have a binding of ethylene. So, call it that it binds like this, and I have hydrogen which binds dissociatively to these transition metals. So, I have a hydrogen here and a hydrogen here. So, both of these bind. Now, a collision on the surface means that this species here, this species which is bound here must collide with this, and the collision frequency when two things are bound is going to be smaller than if they were out here. So, the gas phase collision here is going to be much higher than the collision that we have between two species which are bound to the surface. So, although EA catalyzed, although it is less than EA uncatalyzed, A catalyzed, that is the pre-exponential factor, is less than A uncatalyzed. So, effectively log K cat will then be proportional to so you may not get the complete enhancement in the rate constant that you expect if you believe that this is the same as uncat. So, you will get something which is a little bit or faster because this increase is offset by a decrease in this quantity. So, that is what happens, and this mechanism that you have is called the Hinshelwood, the Langmuir-Hinshelwood mechanism. So, the Langmuir-Hinshelwood mechanism in the general case, I have discussed this for the specific case here. The general case, imagine that I have a reaction N2 plus 3H2 giving you 2NH3, two diatomic species happening on the iron surface. This is the Haber-Bosch process. So, if I have a surface like this, so I have the iron surface, and on this iron surface nitrogen gets dissociatively adsorbed, the hydrogen also gets dissociatively adsorbed, and then there is a reaction between this to give you NH adsorbed. So, after a reaction happens, you have NH that is adsorbed. The NH adsorbed will then react with another hydrogen which is beside it to give you NH2 adsorbed, and the NH2 adsorbed will react with another hydrogen which is beside it to give you NH3 which is adsorbed, which then desorbs. So, if you wrote out all the steps for the N2 plus H2 reaction, this is how it goes. So, N2 gas will bind to the surface to give you N adsorbed onto Fe. H2 gas will adsorb to the surface of iron. The hydrogen and the nitrogen that are adsorbed on the surface will react to give you NH adsorb, and then this goes on. Goes to a next step, and then a third step. And this adsorbed ammonia then will desorb the ammonia to give you ammonia in the gas phase. That is the series of steps that happens in the synthesis of ammonia from nitrogen and hydrogen on iron surface. the Haber-Bosch process. This got the understanding of the mechanism for the reaction of N2 plus H2 on the iron surface got Gerhard Ertl the Nobel Prize. And you will notice this is an example of the Langmuir-Hinshelwood mechanism for surface reactions. There is another possibility that you can imagine, and that is a different mechanism. You can have N2 gas plus the iron surface gives you adsorbed species, and then the adsorbed species could react with hydrogen in the gas phase to give you an adsorbed species, and then this could go on. This is a different possibility and this has been ruled out. So, this does not happen. So, this is an example of the Langmuir-Hinshelwood mechanism, and that is what works in the case of the ammonia reaction. You can have other possibilities where you have one species that is adsorbed and the other species is just in the gas phase to give you a reaction, but this does not happen. It is a very uncommon mechanism, but it has been observed in a few instances, and this mechanism is called LA radial due to the two scientists who first proposed it, and it has been observed in a few cases, but it is much rarer than what you have in this particular case. So, this one in the case of ammonia required detailed study, which got Gerhard Ertl the Nobel Prize. So, one of the things that you would have observed in the Langmuir-Hinshelwood mechanism is that chemisorption is an important step. In the catalysis, because you have adsorbed species like this. If you take nitrogen gas and you want to get two nitrogen atoms in the gas phase, this delta H is of the order of around 1000 kilojoules per mole, and for hydrogen gas this is also very high. (250 kilojoules per mole), maybe even bigger than this. But this adsorption here happens without very much of an activation energy. This one has no activation barrier. And this one has an activation barrier of about 20 kilojoules per mole. So, rather than break nitrogen and hydrogen in the gas phase, which requires lot of energy, what you have achieved by having the iron surface is breaking of the hydrogen and the nitrogen bonds. So, these are some of the strongest bonds that you can imagine, the H2 bond and the N triple bond N bonds. These two are very strong, but by having a catalyst surface you have essentially short circuited this. So, you do not have to spend so much energy as is given here, but with much lesser energy you are able to get adsorbed species, and that is the driving force. That is what makes this surface reaction much faster than what you would have if you had it in the gas phase. So, if you now looked at various catalysts, so if you looked at the rate of this reaction or the rate constant of the reaction as a function of catalyst, so let us look at the first row transition metal elements. As you move along this, so you have different transition elements here. As you move along this, the heat of adsorption will keep on as you move across the table, you will find that when the adsorption is less, that is, the well into which it falls is less, the rate constant is small. And as you move up, these rate constant increase until you reach an optimum point, after which it will start to decrease. So, there is this sort of what is called a volcano plot. So, here you have poor adsorption, and here you have strong adsorption. So, either when you have poor adsorption or when you have strong adsorption, the rate constant is not optimal. When you have poor adsorption, the rates are too low, and when you have strong adsorption, what happens is, once this is formed, because it is in a well, these do not want to react. Whereas, in this situation, you are not binding tightly enough, so there is not enough time for these two things to collide on the surface. Before they collide, they come off from the surface. So, that is the problem that you have. When you have poor adsorption, the rates are too slow, and when you have too strong an adsorption, also the rates are too slow. So, you want some optimal adsorption, and that if you looked at for some reaction as you go along the first row transition series, you get this kind of behavior. This was done for ethylene hydrogenation by a French scientist called Paul Sabatier, who got the Nobel Prize for olefin hydrogenation. And you get this volcano kind of plot, and this volcano plot is a clear indication that you have what is called contact catalysis. So, some of the things that are important for us if you are interested in catalysis is selectivity, and here is a case which illustrates this. If you look at the conversion of ethanol vapor at 600 Kelvin in the presence of various catalysts, I have listed it out here. In the presence of copper, I get acetaldehyde and hydrogen. With alumina as a catalyst, I get ethylene and water. With magnesia and silicon dioxide with sodium oxide as a promoter, I get butadiene and water. And in the presence of what is called a zeolite catalyst ZSM5, I get synthetic gasoline and water. So, for the same reactant under identical conditions for different catalysts, I get different products. Imagine that I am interested in producing butadiene from the decomposition of ethanol vapor. And if I did this, I would choose to do this with magnesium oxide and silicon dioxide. But when I do this reaction, I get butadiene and water, but if you looked at the product, you will also get the other things. You will get acetaldehyde, you will get ethylene, you will get synthetic gasoline as well as the product that you are interested, which is butadiene in this case. And so, one is interested in what is called the selectivity. So, for the number of moles of reactants consumed, I am looking at how much of the desired product I get. So, imagine I started with 1 mole of ethanol. If I get 0.8 moles of butadiene, then the selectivity of magnesium oxide, silicon dioxide with Na2O as a promoter would be 80%, because it will be 0.8 divided by 1 times 100. So, this is a measure of how well or how selective a catalyst is for a particular reaction, right? Because I am interested. So, imagine that I am interested in this. So, moles of butadiene formed over moles of reactants consumed into 100%. And if I looked at the product, I will get this, but I will also get this. You can't completely rule out the other products. You will get the other products too, but you get at least 80% of this. So, selectivity, ideally you would like to see 100% selectivity, where you get only the product that you want and not any of the other products you wish to not have. If you can achieve 100% selectivity, then you have achieved a great thing. So, selectivity is very, very important when you are looking at catalysts. And as this illustrates, you can have different catalysts for the same reactant give you different products. So, selectivity is a crucial thing when you are doing industrial catalysis. The other thing that is important for us is that when you look at catalysts that are of industrial use, when you use it repeatedly, the catalyst will get deactivated. Deactivation could happen for various reasons. It could be thermal, it could be mechanical, it could be chemical. The thing that often happens is when you have a reactant, you not only have your reactants, but you also have impurities in this. And if the impurities in the reactants go and bind to the catalyst and they bind stronger than the reactants, then the catalyst surface is poisoned by the impurities, and so the surface is not available for reaction. So, that is one possibility. So, this is a chemical reason. Fouling is a mechanical reason where physical deposits. So, you have something on the surface and when you have reactants, things physically deposit on the catalyst. So, this is a mechanical thing that happens. Now, most heterogeneous catalyst reactions that are happen in industry happen at reasonably high temperature. And if your catalyst does not happen to be stable at those temperatures, the catalyst will undergo a phase transformation. It will go into a different form which does not catalyze the reaction. So, thermal stability is also of great importance. So, when the catalyst degrades, the catalyst surface area is decreased, that is available for catalysis, and as a result that the reaction rates go down. Again, something which is related, although this could be considered as a chemical thing that happens, is as the temperature is raised of the catalyst, the vapor pressure will increase. So, the catalyst will then vaporize and resulting thing is that the surface area will decrease because of this volatility. Similarly, you can have gas solid reactions and solid reactions that happen, which give you some inactive phase leading to reduced catalysis. And the last that happens is similar to thermal degradation, except that when you heat, very often there is a compaction that happens of the catalyst, which leads to a decrease in catalyst surface area. So, all of these could cause deactivation of the catalyst. The thing that we would like to look at is the chemical reasons for catalysis being poisoned. Here are various examples of impurities that poisons catalysts, and in the ammonia synthesis where you are using iron, any of these could poison the catalyst. So, your reactants have to be so purified such that these do not figure in the input stream to cause poisoning of this. And I have listed here various chemical processes, the catalysts that are used here and the kinds of impurities that do affect the rate of the reaction, right. And you will see some things here. You have gases, you have oxides of carbon, you have sulfur. Sulfur you will see is a common thing that figures in many of these because you have hydrogen sulfide in both of these, arsenic. So, these are things that will bind to the surface and cause poisoning of the catalyst. And these are various examples. I do not think you need to memorize it, but you get the general idea. For different catalysts, you can have different poisons, and poisons affect the catalytic performance. And so, you want to make sure that poisons are not present in the reactant phase when you do this reaction. So, with this, I think we will stop the general discussion about heterogeneous catalysis. There are two further things that we will need to look at. One is zeolite catalysis, which I will discuss next. This is something that you might have encountered in your study of inorganic chemistry. Zeolites, you must know of the silicate tetrahedra. So, this is the silicate tetrahedra, and you have extended structures of this, and that gives you silicon dioxide quartz or sand or whatever. So, if you do this, you extend this. So, you take one of these, I will give you an example. And I could go on. Right. So, this can go on. So, this is a silicate that you have got Si2O7. Now, I can take a silicon tetrahedra like this, join this together, and every once in a while I replace some of these silicate tetrahedra with aluminate. That will be AlO5, AlO4 5 minus. So, these are silicon SiO4 4 minus, and here you will have AlO4 5 minus. So, what you do is you take this silicate tetrahedra which are joined together, and you replace every once in a while. So, you will get something like this. So, when there are only silicate tetrahedra, there is no charge essentially, but the moment you have this, you saw that it is AlO4 5 minus. So, this has to be balanced by a positive charge. So, you have a metal along with this. So, this now can form cages. So, you could have cages like this, where you might have already encountered this in some form. And you fill this up. You must have seen this. So, you have similar kind of network, except that every once in a while you replace this with alumina. So, these are zeolites, and these can have structures with cages in it. So, you can imagine this situation, except that you put a lot more of these silicates, replace every few of them with alumina, and you will get cages like this. And as you can imagine, there are positive charges on this. So, the silica alumina network that you have got has Lewis acid sites, and this Lewis acid sites arise as a result of the aluminum which is outside this framework. So, these are your zeolite structures, and they form cages into which you can trap, these cages trap reactants. And you have, if this positive charge is an H plus, then it happens to be a Bronsted acid site. Whereas, if you have extra framework alumina, then you have Lewis acid sites. So, these zeolites happen to have cages which can trap reactants, as well as Bronsted and Lewis acid sites. So, these are very good catalysts for many of the steam reforming reactions that is used in the petroleum industry for getting cracking of petroleum, and they work through these cage formation which traps species. So, this is a large class of catalysts which are called zeolites. And the thing to understand is that they are formed by a network of silicate and aluminate tetrahedra joined together to form cages in which reactants are trapped, and there are both Bronsted acid sites as well as Lewis acid sites which allow the catalytic power of the zeolites to come into place. So, that is one class of catalysis that we needed to look at. The other thing that we need to look at is enzyme catalysis. Now, enzymes are polymers, and you might have encountered this in your study of organic chemistry. These are polymers with amino acids as the monomers. What are amino acids? If you have a molecule with this general formula, this is an amino acid, this is an amine, and this is a carboxylic acid. So, this is a particular class of amino acids that we are looking at, and there are these R's can be 20 in nature. So, there are 20 different R's, and you take one amino acid like this, you put it beside another amino acid where I have a different R, call it R prime, and now I lose a water molecule from here, and if I lose a water molecule from here, I have what is called a dipeptide, which looks like this. And there is no reason for you to stop here. You can add other amino acids and you build a long chain like this. So, this is a dipeptide, and if you did this infinitely, you will get what is called a protein, and enzymes are proteins. And what happens is, because of restricted rotation about these enzymes have very interesting shapes. So, you could have enzymes which look like this. So, this is made up of these polypeptide chains which curl up to give you some very interesting shapes, and this is what might be called an active site of the enzyme. Okay. Now, these enzymes are very, very efficient catalysts. They are present in our body and they catalyze a whole set of reactions, and here is how they are classified. So, the enzymes are classified based on their action, and I am listing here some that there are 6 different classes. If I have a reaction which goes AH2 plus B, where I have a transfer here, then this is called an oxido reductase, and here is an example of an enzyme which does this kind of reaction. In this case, I have the X group which is transferred from A, it is attached to A in the reactant side and it gets transferred to B. So, if X happens to be an amino group, then it is called an aminotransferase. The third kind, which is very popular, is if I have a molecule AB and I want to cleave this bond with the presence of water, I can get AH plus BOH. So, this is an example of a protease and so on. And there are 6 different classes that is typically observed of the kinds of reactions that these enzymes do. And here are the various examples for each of these categories. But the important thing for us to realize is that whatever enzyme you have, these are all made up of these amino acids which are put together one after the other. And a simple way of thinking about it is, think of each of your R's. So, think of each of these amino acids let me just think of this amino acid as a bead. Okay, call this a red colored bead. And if I have a different R prime, let me call it R prime, let me call it a square bead. Now, I put these two together I join them and I get something, and I keep going like that. And I can put various things together. So, think of this as a necklace, and I have this long chain. And you know, when you have a long chain, long necklace with different size beads, different colored beads, when you put it, it does not take the shape of a linear thing. It does not sit like this. What it does is it folds up, and when it folds up, it takes a very strange shape. And based on what you have here, so it could be blue, red, black, blue, blue. But if I have a different order, then the shape it takes is different. So, based on what I have here, what are the beads which I have put together, the shape that the enzyme takes is finally very different. So, I could have something which, so imagine that I have an enzyme which folds up in such a way that I have something like this. And if I have a molecule that has this shape to it, so imagine that I have a molecule like this reacting with a molecule like this. What happens is, these two molecules will come and bind to the enzyme. When they bind, what happens initially is that the binding is not very good, but the moment there is some amount of binding, the molecule, the enzyme, will twist in such a way that it will enhance the binding between these two. And so, you will get, now let us see if I can draw the same shape again. So, now it is bound. And once it is bound, I have a reaction between these two species. So, this enzyme, the blue enzyme which has this strange shape, gives the opportunity for these two things to bind. So, the way this reaction works is that, called this, so in the terminology of enzyme kinetics, this enzyme is represented by E, and these two things are called the substrates, called this S1 and S2. So, what happens is, initially the enzyme binds the substrate. So, I will get an E plus S will bind and I get an enzyme substrate complex. I have a reaction of this enzyme substrate complex to give you a product, call it the enzyme product complex, and then this goes away and you will regenerate the enzyme and give back the product, and this cycle repeats itself. So, I have the enzyme and I have the substrate to give you an enzyme substrate complex, undergoes a reaction in the presence of the enzyme with the substrate bound to the enzyme, gives you an enzyme product complex, which then falls apart to give you the enzyme and the product itself. And if you drew the Gibbs energy, the energy versus the reaction coordinate profile, it's identical to what we had in the case of the catalyst. So, let's imagine that I have this reactants, I have products. What we are saying is there's an enzyme substrate complex, the enzyme product, and this. So, this is the uncatalyzed reaction. This corresponds to the enzyme substrate complex. This corresponds to the enzyme product complex, and this gives you back the product. So, this reduced energy barrier, so this activation energy that you have got for the reaction on the enzyme is much lower than this, and this leads to extreme efficiency for the enzyme catalyst reactions. And the efficiency of enzyme catalyzed reactions is characterized by a quantity which is called the turnover number, and I have listed some of the turnover numbers here. Carbonic anhydrase is by far the most efficient enzyme that you can think of. This enzyme catalyzes the reaction of carbon dioxide with water to give you bicarbonate, and what this tells you is that per second 600,000 molecules of carbon dioxide and water combine to give you bicarbonate. This is more efficient than any catalyst that a human can synthesize so far. This is very, very efficient, and I have listed here, no reason again to remember all of these. All that I am trying to do is to give you an idea that some of these turnover numbers, which is a measure of how many molecules per second a reactant gets turned over into a product, and more the number, higher is the efficiency. And you can see that as you go down here, you have various enzymes. This is by far one of the most efficient enzyme, and as you go down, the number keeps on decreasing. So, enzymes are extremely efficient. Our whole natural system, our body for example, completely works with enzyme catalyzed reactions, right. Penicillinase for example is the enzyme that breaks down a penicillin antibiotic which is given to the body. So, this breaks down the penicillin antibiotic. Lactate dehydrogenase is what acts when you drink milk for example. So, all of these enzymes are things that are present in the body, and they have various levels of activity. There is of late there is also use of enzyme for industrial production of compounds, and there are advantages and disadvantages for enzyme catalyzed reactions, and they are listed here. They have very high enantioselectivity, and you can imagine this because you have these enzymes and they have these strange shapes, And obviously, even if there is a small change in the reactant that binds, the enzyme will be unable to bind that thing, and if there is no binding, then there is no reaction. So, they have very high enantioselectivity, they have very high regioselectivity, which means that if you have a reaction at one site, it won't react if there is a change in that. And you can have reactions happen at very mild conditions. This is of great importance because you don't want to subject your reactants to harsh conditions. And since the enzymes contain proteins which are amino acids and they are available in nature, they don't work under harsh conditions. So, most enzyme catalyzed reactions happen under very, very mild conditions. So, the other big advantage which is becoming increasingly important in recent days is that the enzyme catalyzed reactions happen in a water medium. This is very important because nowadays we are interested in what is called green chemistry, because you want to minimize the amount of bad things that you put into the environment. So, any reaction that happens in a water medium is preferred over something that happens in an organic medium. So, this is of great importance. So, people are trying to design catalysts which will work under conditions of when in water medium. So, and all enzyme reactions, because they are natural polymers, exist only in water medium. So, this is naturally enzyme reactions happen in water medium. There are disadvantages to it in that it has very low specific activity, and because these enzymes are proteins which contain natural amino acids, the moment you raise the temperature, these proteins denature. And you have seen this protein denaturation. If you take an egg, the eggshell, after you boil it, has undergone a change. What was solid initially, but when you boil the egg, it undergoes, the shell becomes hard, and there is a denaturation process. And that is an example of a protein, or in this case a protein, and since all proteins are enzymes, they undergo denaturation, which means that the active configuration of the protein is changed. Similarly, the amino acids contain groups which have either basic or acidic side groups, and they have a specific range of pH over which they act. So, this limited temperature and pH range of activity, when you go into industrial setting, becomes a disadvantage, although normally it is an advantage. The other thing that you have to notice is that enzymes only catalyze a limited set of reactions. You can't imagine every conceivable organic reaction have an enzyme catalyzed equivalent. People are working towards it, but as things stand, there are very limited set of reactions that you can use for enzyme catalyzed studies. And from an industry standpoint, the biggest problem is that if you try and develop an enzyme to do a particular reaction, before it becomes marketable, it takes a long development time and extreme expenditure. So, this is one of the reasons why the use of enzymes has lagged behind in industry. But as the push for green chemistry, that is reactions in a water medium, takes precedence, you are going to see more and more reactions which are enzyme catalyzed. And the enzyme catalyzed reaction, as we have seen, is very straightforward, and it is an adaptation of what we saw in heterogeneous catalysts. I will just recap this before I close for the day, and that will close the subject of catalysis. So, this is how it goes. you have an enzyme, it grabs a substrate to form an enzyme substrate complex. This enzyme substrate complex will undergo a reaction to give you the product which is still bound, and the enzyme product complex then falls apart to give you regenerate the enzyme, sorry, this is not right, and the product. And this is how it works. This is attributed to two scientists. This mechanism is called Michaelis and Menten. And if you looked at the rate of the reaction of these enzyme catalyzed reactions as a function of the substrate concentration, you will find something which goes like this. So, typically in all enzyme catalyzed reactions, you will see the rate variation with substrate go like this. So, with this I think I will close for the day. What we have looked at today is how a heterogeneously catalyzed reaction works. We discussed the Langmuir-Hinshelwood mechanism, where you have contact catalysis, where you have two reactants which come and bind to a surface, and then I have a reaction on the surface, which means that although the activation energy is low, the number of collisions are also low, but they are somehow offset each other. And typically we also said that the extent of binding has to be optimal for having the largest rate constant. Either if it is too low or if it is too high, then the rate constants are suboptimal, and that is because of adsorption phenomena. And then we looked at briefly zeolite and enzyme catalysis. With this, we will close for the day. In the next session, we will look at colloids, which will close this discussion on surface chemistry. Thank you.